Going? This is Mike coming back at you with another video on discrete mathematics. In the previous video, we just went through a couple more basic definitions of some mathematical facts, and we went through a couple types of functions that we have out there in the world of number theory, and then a really basic yet important theorem in the world of number theory as well. In this video, we're going to go through several sample proofs. We're actually going to look at the setup, the structure of these proofs, and we'll see how they compare to the three-step method of direct proof that I told you about a couple of videos back. So we'll get right into it. You could be asked to show that or prove that, show that, prove that, in the context of having to prove something means the same thing. We're going to show that the sum of two odd integers is even. So if you have two integers, a and b, say, each of those are odd, when you take their sum, we're going to show that that sum is even. Now, the first step in our three-step process, which was kind of an optional step, is to take the sentence, which states what you have to prove, and write it in a more logical form, put it in that universal kind of context. So this one might be a good sample to see where we would use that that first step here. The statement is again saying, show that the sum of two odd integers is even. Another way that we can say this is for all integers, and we're going to need two of them, so let's just give them some arbitrary names. Let's call them a and b. For all integers a and b, and now what follows that quantifier? We want to put this as an if and then statement. We want to put this as a conditional. So the way that we can say the sum of two odd integers is even as a conditional statement for these two integers a and b is that if a and b are odd, then a plus b is even. That's the way that we take the sum of two odd integers is even, and we transform it into a conditional. So in a more logical form, as a quantified statement, we can say that for all a and b in a set of integers z, if a and b are odd, then a plus b is even. So that's a way that we can take the given sentence and write it as a quantified statement. We have the for all, and then we have a conditional following after that we want to show that this is true. So this was our step one, the optional step, but a pretty good case here where we might want to use that just to make it more clear as to what we are trying to do here in this proof. The second step is to suppose that you have a particular yet arbitrarily chosen element, or in this case, elements of your domain. In this case, our domain is the set of all integers or the set of all whole numbers, and we're working with two such numbers, so we call them a and b. Now, let me just clarify the particular yet arbitrarily chosen. We only mean particular in the sense of how many we are working with in this proof. We are working with two particular integers. However, when we say arbitrarily chosen, we mean that they could be any integers that make our hypothesis true here. So we're not specifically picking, say, 5 and 7 or 13 and 21. We just have two whole numbers, A and B, and we're going to assume that the hypothesis, or we're going to assume that the predicate here, or the hypotheses, sorry, are true here, and we're going to assume that A and B are odd integers. So we can say this really short and sweet. Notice that I just labeled the start of my proof with proof. You don't have to do this, but it's pretty common that you'll see this happening inside of math textbooks, so it never hurts. Instead of using A and B, I chose to use M and N. Ultimately, it doesn't matter what names you give to those guys. So I let M and N be two integers, and I said let them be odd. In the notes, I know that instead of the word let, I had the word suppose. That's perfectly fine. I also could have said suppose M and N in Z are odd integers. It would be saying the same thing. But big thing is we chose, in this case, two particular yet arbitrarily chosen whole numbers, and we've assumed that they're odd because the assumption that they're odd was our hypothesis that we saw from our more logically written and quantified statement back in the previous slide. So this was step 2. You have your particular yet arbitrarily chosen guy or guys in your domain, and you've assumed that your hypothesis or hypotheses are true. You're now going to then use basic definitions, basic theorems, basic math facts to show that the conclusion has to be true. We want to show that A plus B is even. Okay, well, let's think back a couple videos. We gave definitions of what it means for an integer to be even or odd. We said that an integer was odd if it can be written as 2 times some whole number plus 1. So since m is odd, m is equal to 2r plus 1, where r is some whole number. And then also n was odd, so we can write n as 2 times s plus 1, where s is, again, some whole number. We don't know what that particular whole number is for r and s. That would be based on what the m and n values would be. But again, these are freely chosen odd whole numbers here. So these proofs that we're going to do, they're going to be very low level, very basic. We're going to see that once we use 1 or 2 basic definitions or facts, we'll see that we can then do a very nice, easy, and pretty much trivial mathematical operation to arrive at our conclusion. So these are not going to be very high-level proofs, really complicated things. You'll see those if you go on to take future math classes. But I have something for m. I have something for n. Let's just try to take the sum of m and n, and we'll see if we can get this thing to be even. Recall that an integer is even means that it can be written in the form 2 times some whole number. So if I do m plus n, I have 2r plus 1 plus 2s plus 1. I just made the substitutions for m and n on their own. When you simplify all that, that gets me 2r plus 2s plus 2. And note that every one of these terms has a common factor of 2, so I can pull that 2 out, leaving me 2 times the quantity, r plus s plus 1. Now, it goes pretty much without saying, you may assume that differences, products, and sums of integers are going to be integers as well. So I have this r plus s plus 1. This is all some whole number. So I rename this thing q. So I've shown that m plus n is of the form 2 times q, where q, which is the r plus s plus 1, is some whole number. So what I've done here is I've shown that m plus n is equal to 2 times some whole number. By definition, that means that m plus n is even. And thus we've shown that the conclusion has to be true. We've used basic definitions and just basic mathematical operations to show that if I have any two particular yet arbitrarily chosen odd whole numbers, when I take their sum, I get a number that's even. So we're going to do another one that's similar to this. We're going to show that the product of two odd integers is odd. Again, maybe you want to begin this by writing it in a more logically quantified form, actually putting the quantifier in there and then writing a conditional right afterwards. If you do that, I should say if you want to do that, the way that you can write this one is to say for all m and n in Z, because again, we are working with whole numbers. We want to show that the product of two odd integers is odd. So for all m and n in Z, if m and n are odd, then we have to show that the product is odd. So we have to show that m times n is odd. Now let me see if I can fix these here. It looks a bit better. Yeah, so this is a way that we can write the given sentence in a more logically quantified form. So again, we are going to move on to step 2 now. Suppose that we have a couple particular yet arbitrarily chosen integers, m and n, and we're going to assume the hypothesis. We're going to assume that m and n are odd. So we're starting this off exactly the same way as we did with our previous proof. Now we want to get to the conclusion that the product m times n, we want to get to the conclusion that this product is odd. So going back to where we left off at, we just completed step 2. Now we have the meat of our proof. All the work that shows us, okay, we got to the conclusion, and here's why this thing has to be true. We're going to use the definitions of an odd integer once again. So again, same thing as with our previous problem. M is of the form 2r plus 1, and n is of the form 2s plus 1, where r and s are whole numbers. This is yet another really basic, very low-level proof. We're just going to do a basic mathematical operation, and this should give us the calculation that we want to see. We should be able to easily take m times n and see that we can write it as the form 2 times some whole number plus 1. So m times n if you just FOIL 2r plus 1 and 2s plus 1, you get 4rs plus 2r plus 2s plus 1. Now these first three terms here, they each have a common factor of 2, so I'm going to pull the 2 out of each of those three terms, and then we still have the plus 1 at the end. So that puts me right here. Again, sums and products of integers are going to be integers as well. So this whole thing here is some integer, which I called q. So I can make the substitution there for q, and this is of the form 2q plus 1. My apologies, there's a typo there. So this is going to be of the form 2q plus 1. So we have shown now that if I have any two odd integers m and n, when I take their product, I get something of the form 2 times some whole number plus 1. And by definition, that says that the product, m times n, is odd. So these were just a couple really basic, very low-level problems just pertaining to integers being even or odd and how certain combinations of them result to be even or odd. But again, focus on the three-step process that we're using in this method of direct proof. Again, the first step, that's optional. Take your given sentence or statement that you have to prove, rewrite it as a quantified statement involving a conditional. Then set up your proof. Let one guy or two guys be arbitrary guys from some set, and then use basic definitions, facts, theorems to arrive at your conclusion. Also in step 2, you're assuming that your hypotheses are true. So here's the third one. In the previous video, we talked about what it means for a number to be a rational number. So we're going to show or prove that the sum of two rational numbers is a rational number. Sometimes for short, you'll just see the sum of two rational numbers is rational. So now, once again, we'll do one more here where we actually take a look at the given sentence as a quantified statement. So for all m and n in... Now, the statement says the sum of two rational numbers. So we're working in the set of all rational numbers here, which is that fancy / weird looking Q. And this is a little bit redundant. You could write this as a conditional. It would be a bit redundant because what your hypothesis would be is saying that if m and n are rationals, which we have just assumed, or which we've just stated in the use of our quantifier here. So you could restate that if m and n are rationals, then m plus n is rational, but you don't necessarily have to do that. But because most of these things will be in a conditional format, we will essentially repeat ourselves and write this as a conditional. So if m and n are rationals or are rational, then m plus n is a rational number or is an element of Q. So again, this particular sentence here that we have to approve, writing it as a quantified statement, a little bit different, a little bit odd. but sometimes you encounter those, and you just kind of have to work with them. So I'm going to kick off my proof by assuming I have two particular yet arbitrarily chosen rational numbers. I'm going to stick with m and n here. Now, the end goal is to show that m plus n is a rational number as well. But first, let's take the fact that m and n are rationals on their own and essentially state what that means. What is the definition of a rational number? From our previous video, we said that a rational number is the quotient of two whole numbers, and such that the number on the bottom is not zero. So I can say that m is of the form a over b, where a and b are integers and b is not zero. And also I can say that n is of the form c over d, where c and d are whole numbers and d is not equal to 0. So we're just using the basic definition of what does it mean for these things to be a rational number. So now let's try taking the sum and we'll see how we can come to the conclusion that we want to come to. So m plus n is simply a over b plus c over d, but I want to turn this all into one fraction because this right here is not helping me. Just leaving a over b plus c over d is not putting this in a form that I can verify the two things that I need to verify to know that I have a rational number. So we find the least common multiple between the two bottoms, and you come up with AD plus BC all over BD. So there's two things we have to check. We want to make sure that m plus n is a rational number. We want to make sure that this thing is a rational. First thing we need to check, are the top and bottom whole numbers? Well, A, B, C, and D are whole numbers. So again, products and sums of whole numbers are whole numbers. So yes, the top and bottom on their own are whole numbers. So that's good. Other thing we have to check, is the bottom not zero? Well, we specified earlier on in our proof that B is not zero and D is not zero. So when I take the product of two things that are not zero, you may assume, because it's pretty much common knowledge, that you cannot get zero. There is no way to take the product of two things where each thing is not zero and come up with zero. That's just not possible. So yes, BD is also not zero. So we verified the two things that we need to verify to show that we have a rational number here. So m plus n is rational, and therefore the sum of two rational numbers is rational. I didn't have to include this last sentence here. This is something that people like to do in some cases. This is really just your own personal preference. If you want to end your proof by restating what the fact was, that's fine, but not something that you have to do. One more that we're going to see here. This is in regards to divisibility. We talked about that in the previous video as well. Prove that if A divides B and B divides C, then A divides C. And since we're talking about this in the context of divisibility, we are talking about integers here. We are working with whole numbers. So that is a little bit of the context of the question that you're in. something that on a quiz or test I would clarify. You wouldn't necessarily have to just pull that off the top of your head and say, okay, we're working with whole numbers here. So this is a little bit more clearly in a form that we can write a quantified statement for. It's a little bit clearer and a little bit less of a jump to write this as for all A, B, and C in the set of integers. If A divides B, try to make that a bit neater. A divides B, and B divides C, then A divides C. The conditional statement is just given to us right in that sentence. It's really easy just to copy that over. But that's the quantified statement. So we're going to assume or let or suppose we have three arbitrary integers A, B, and C, and we're going to assume that A divides B and that B divides C. Now, thinking back to the previous video, what does it mean by definition for A to divide B? And also by definition, what does it mean for B to divide C? Well, since A divides B, by definition, B is equal to A times some whole number M. And then since B divides C, C is equal to B times some whole number N. Those are just the straightforward definitions of what it means for a number to divide another number. So I want to show that A divides C. And this is something that you may want to write on the side of your own piece of paper just for your own sake, just to help you kind of have a little bit of like a guiding light at the end of the tunnel, so to speak, just to help you see where you want to get to in the end. We want to show in the end that A divides C. So what we want to show, or WTS, we want to show that C is equal to A times some whole number, I'll call it P. So C is equal to A times P, where P is, again, some whole number. So that's something like what we want to get to at the end of this proof. And maybe looking at it like that provides a little bit more clarity as to what we have to do. Here I have C in terms of B. Here I have B in terms of A. If I make this substitution in for B, then I have C in terms of A. So I have C is equal to A times M times N, and that's equal to A times M times N. So I now have C equal to A times some whole number. Here I called that whole number Q. You could have called it P. You really could have called it whatever, as long as you didn't use A, B, or C, or M, or N. Any other letter, though, doesn't matter. So I've shown that C is A times some whole number, which means that by definition, since C equals A times some whole number, that is the definition of A divides C. So we have reached our conclusion. We've shown that this is true. You'll be seeing more sample problems like this in practice problems, for homework, on quizzes and tests as well. So you will be getting more practice with these guys. There's no one particular right way to write these proofs. As long as you're pretty much following the same three-step process, and you are writing things so that I can understand what it is you're trying to say, then you'll be good. We're not going for picture-perfect proofs here. This is just getting our feet wet. In the next video, we will do more proofs, but we'll prove facts in a little bit of a different way. We'll see how we use these alternate methods to prove facts or to prove statements. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.